1 month, so I hope to have some discussions with many of you while I am here. Please feel free to come and see me anytime. All right, so I think this is supposed to be more of a graduate mini course than a seminar talk. So my plan is to give maybe some details of some things. Maybe not every detail of everything, but some details of some things. And also even to give a few exercises. So to keep the students busy, I will mention some exercises as we go along. Okay. Oh, and of course, you should ask me questions. So it's more of a mini course than a seminar talk, so you should ask lots of questions. Maybe I can answer some of them. Okay, the topic in general of all the lectures is nonlinear Schrödinger equations of various types. Probably many of you are somewhat or very familiar with nonlinear Schrödinger equations. And so I don't have to give a big justification as to why we should spend lots of time studying nonlinear Schrödinger equations. But just to mention very briefly, of course, nonlinear Schrödinger type equations come up in many places in physics, all kinds of applications. Just to mention a few, quantum mechanics, especially many-body quantum theory. Optics is a famous one, where nonlinear Schrödinger plays a role. One that's maybe slightly less well known, but by the end of today will be much better known, is ferromagnetism. And one can go on. There's superfluids. So there's no shortage of physics reasons to study nonlinear Schrödinger type equations. But somehow mathematically, one thing we always have in mind when we're looking at equations like this is that we're trying to understand phenomena. So if you want to understand something about the general phenomena of dispersive but nonlinear waves, then nonlinear Schrödinger equations are a natural laboratory for this. So you might say as a model for nonlinear dispersive waves more generally. So we can understand mathematically what's going on. Okay, of course I'll write some equations as we go. The themes that I'll be emphasizing in these lectures are the following. We will have well, generally speaking, the theme is to try to understand global behavior of solutions as much as possible. So consider the initial value problem for some nonlinear Schrödinger equation. Can we describe what's happening to the corresponding solution for a large class of initial data? That's the goal. More precisely, we'll look at solitons and their stability, so stability of solitons. So solitons, in general, I just mean the basic, usually stationary solution of the equation, whether it's a soliton or something else, which physically you would think of as the kind of ground state, the basic solution. And so at first you want to understand how solutions behave in a neighborhood of these ground states, let's call them solitons. That's the theory of stability of solitons. More generally, we're interested in long-time dynamics. And that's, of course, related to solitons, because if the solitons are the ground states, then somehow you should be able to describe the long-time dynamics in terms of these ground states. And then also related to long-time dynamics is the question of whether long-time dynamics exist or not. So that's the question of whether you have blow-up or singularity formation. Singularity formation or sometimes non-formation. So these are the things I'll talk about for all of the lectures. More precisely, the topics will go roughly like this. There's 3 of them that I want to touch on, at least 3, probably only 3. The first one is what you might call a geometric nonlinear Schrödinger equation, which in physics you would call the Landau-Lifshitz equation. That's one topic, and that's today's topic. So, roughly speaking, this will be maybe lectures 1 and 2. Second topic will be nonlinear Schrödinger equation with potential. Okay, so potential introduces some kind of external force, and the question is, how do, let's say, solitons of the nonlinear Schrödinger equation interact with the potential, with the external force? Roughly speaking, that's the next lectures. And then the last topic is a little bit different than the first 2, has to do with periodic, spatially periodic solutions of the nonlinear Schrödinger equation, periodic waves. Roughly speaking, the last lecture. Of course, this may change dramatically as we go, but we'll see. That's the plan. Okay. So then let me jump right into today's topic. Maybe I start here. Which is this so-called geometric nonlinear Schrödinger equation. More precisely, it goes by 2 different names. It's sometimes called Schrödinger map, and as I wrote before, it's sometimes called Landau-Lifshitz. All right, so let's start with some preliminaries where we discuss the setting, the geometry, and so on for this problem. It'll be a little while before I can actually write the equation, but we'll get there. So let's begin with considering maps between manifolds. So I want to think of a time-dependent family of maps from one manifold, which is going to be actually always R2, into another manifold, well, almost always R2, into another manifold, which is going to be always S2. More generally, the entire discussion I'm going to give here could be generalized to some other Riemannian manifold as the domain. And some other scalar manifold, so a manifold with a complex structure, as the target. And I'm just going to stick to this case. Moreover, even though in geometric problems somehow you really want to try to describe things intrinsically without referring to embedding, but it turns out to be much more practical to consider this, the extrinsic point of view. Put this S2 inside of R3 and just think about unit vectors. So that means I have a unit vector in R3, always. So I have the unit length constraint. Okay, I should put a picture somewhere. Let's put the picture, maybe, okay, put the picture here. So here's S2, sitting in R3. So the next thing I want to do is I want to assign an energy to this map. Very simple. I just take the Dirichlet energy. Okay? Okay? And then I want to differentiate this functional. So I want to compute variational derivative of this energy functional. Of course, everyone knows how to compute the variational derivative of the Dirichlet functional. But we have to do it properly, keeping in mind that our map is taking values in the sphere. So we have a constraint. So here is, say, U, point on the sphere. And so if I want to compute, this is for the graduate students, if I want to compute this variational derivative properly, I have to remember this constraint. In other words, I should think about taking a family of maps depending on some parameter epsilon, which is a variation of some given map U. And then if I differentiate with respect to epsilon, I get a vector, but of course not just any vector, I get a tangent vector. So this is a vector which lies in the tangent space to the sphere. Something like this. And of course, this picture is so simple. For any given vector u, tangent plane is just the orthogonal complement of u. Okay, so I take a variation like this, compute the variational derivative. I should put this one parameter variation inside my energy functional and then differentiate with respect to the parameter. Plug into the Dirichlet energy, and of course you get this. Sum over repeated indices, of course, over j equals 1 and 2. And now we just have to do a tiny bit of geometry. We have to remember that C is a tangent vector. And we should avoid differentiating tangent vectors in the usual way. We should always differentiate tangent vectors covariantly. So in other words, another way to say that, since U is a unit vector, so U is a unit vector, when I take any kind of derivative of U, that's tangent. So that means that any derivative of U is in the tangent space. So this is in the tangent space. but this is not necessarily. And so what I should do is, instead of considering this guy, I should project it back into the tangent space. So I have a projection. Let's call it, let me write it as Pu, which is just the usual orthogonal projection onto the tangent space. And I have this operation of covariant differentiation, where if I have a tangent vector field, I define the covariant derivative of that tangent vector field to be the usual derivative projected back onto the tangent space. And it's easy to work out that this is given by this formula here. So that's how we differentiate covariant. All right, so this is tangent. This is not. So I can project it onto the tangent space without changing the value. So then I get a covariant derivative here. Same thing. And now I can do my integration by parts. Move the covariant derivative, which is anti-self-adjoint, to the other side. And now I see what my variational derivative is. It's this quantity. So taking into account the geometry, the variational derivative of the Dirichlet functional is this guy. It's not Laplacian, but it's Laplacian projected back into the tangent space. And it's simple to work out what that is for the sphere. You get here's your Laplacian, and here's the correction. So that's the variational derivative of the Dirichlet energy for maps into the sphere. And of course, it's not linear anymore. It's nonlinear. And so this is where all the nonlinearity comes from. In all of the problems I'm going to describe today, it comes from the fact that the target manifold is curved rather than flat. As I said before, please stop me at any time if you have other questions. I'd be happy to try to answer them. Okay, maybe I can do this. All right, so that's just energy, that's statics. And now we can finally talk about dynamics. There's a bunch of natural dynamical equations you can associate to this energy. The simplest maybe would be the heat flow. Very classical equation. Harmonic map heat flow. HF for heat flow, some kind of nonlinear version of the heat equation, nonlinear parabolic equation. So there's heat, there's wave. It's called the wave map equation. It's been very well studied in recent years. The wave map, well, I want to make it wave, so I have to take two time derivatives. So I should differentiate here, but I should do so covariantly. So write it this way. It works out to the following. that's the wave map. I'm not going to say too much about either of these. What I'm interested in is the Schrödinger version. To write down the Schrödinger version, I just write down what I think the Schrödinger equation should be, which means I need an I. I need a multiplication by I, which is, if you think about it, multiplication by I is just a 90-degree rotation. So that's what we need to do on this manifold. So we need a 90-degree rotation, also known as a complex structure. So I need an operation which takes this tangent vector here and rotates it by 90 degrees in the tangent space. I'm going to call that J, the operation J. So J, U, maps the tangent space to itself. Tangent vector to, well, think about how you do a 90-degree rotation. It would just be taking the crush product with vector U cross. So that's the complex structure on the sphere. It's very simple. Once I have that, I can write down a Schrödinger type equation. I put the J here and the variational derivative. I think I want a minus here. Doesn't really matter. Which gives me U cross this guy here. But of course, when I take U, if I'm not worried about writing a tangent vector, this will get killed. And this is all that's left. So that equation there is called the Schrödinger map equation. It has some, well, what it looks like is just some general Hamiltonian system. It has some superficial resemblance to the, formal resemblance to the Schrödinger equation here. But when you write it in this form, it's not remotely clear that it's a Schrödinger type equation. We'll see later that it's very much a Schrödinger type equation. All right, so this is my main objective study here today. One other thing you can do, slightly more general, is to write down an equation which is a combination of the Schrödinger and the heat, or if you like, it's the Schrödinger map with some dissipation given by the heat flow. This is very common in the physics literature, and so even though, strictly speaking, this is the Landau-Lifshitz equation, this is called the Landau-Lifshitz equation, what really tends to appear in the physics literature has the damping in it. That would be something like this. So here's the Schrödinger fire. And let's add some heat flow for dissipation. So I'm going to call that equation LL for Landau-Lifshitz. Which equation, I'm sorry? Yes? This one. It looks that way. But you shouldn't take this too seriously. So I'll show you later how we look at this equation, and you'll see how it really looks. In some ways, it's more like cubic NLS. You'll see. This is very misleading. It looks terrible when you look at it this way. Okay, so just before we proceed with analysis, just one word about why we might bother studying equations like this. And as I said before, there's a physical reason. So in physics, more precisely, ferromagnetism, there's some theory called micromagnetics, sometimes called micromagnetics, which is a continuum description of a ferromagnet. And in this theory, this vector U is called the magnetization vector. Which is supposed to describe locally at different places in your ferromagnet which direction the spins are aligned in. That's what ferromagnets, they develop regions where all the spins are aligned in some direction. This vector is recording that, the direction in each location in space. And then what the Schrödinger map equation is saying, which is written down actually by Landau and Lifshitz in the 30s, I guess it was. Schrödinger map says that the magnetization vector undergoes precession in some effective magnetic field. Which is given by the Laplace. That's a very superficial and vague way of describing the physical origin of this equation. If you want to do something slightly more precise, think about having a collection of classical spins, so unit vectors, on a lattice. And each of these spins is going to undergo precession in an effective magnetic field, and the effective magnetic field is given by the average of the neighboring spins on the lattice. And then you pass to a continuum limit. The average becomes the Laplace. That's a slightly more precise way of thinking about where this equation comes from. And I would like to say that this equation genuinely appears in many places in the physics literature. It's a really widely used model for ferromagnet. And so I would argue that this Schrödinger map equation is every bit as physically important as, say, the wave map, which has generated much more mathematical literature so far. I understand the wave map has, well, the wave map was originally sort of a toy model in particle physics, but it does have some connections to general relativity. But I would argue that in terms of being an honest-to-goodness physical model, the Schrödinger map or Landau-Lifshitz is just as good. With the one caveat that in the physics literature, you would usually see this equation with a slightly more complicated energy functional. So you have this isotropic, it's called the exchange energy, this averaging of the neighbor's energy. And then there would typically be other terms as well, anisotropy, external field, some other terms. But this is still the basic model. So I think we're justified in studying this equation every bit as much as studying the wave map equation. Please.
Is the difference between Schrödinger map and Landau-Lifshitz not the two equations?
Is there a difference between these two? Very big difference. So here I put in some dissipation. So this is a purely conservative equation. It's a wave equation, basically. This is a parabolic equation. This one, I haven't said it yet, I'll say it in a moment. This one conserves energy, this one dissipates energy. So mathematically, analytically, there's a huge difference between these two equations. Although they have similar behavior in many respects. They have the same scaling, for example. So one can actually learn a lot about what might happen for the Schrödinger case by looking at the Landau-Lifshitz case, or even the heat flow. In fact, it's not a bad way to predict phenomena. But mathematically, one is parabolic and one is hyperbolic. So they're quite different. Okay.
Excuse me.
Yes, please.
The direction derivative with respect to u, the d alpha u,
This one here.
the second line, zero, is the d xi is s zero, the last line s is the d xi or d u. It's projection.
So this is projection.
Projection
So
of d xi
I'm projecting this
tangent space.
vector back into the tangent space. So I'm subtracting this dot u times u. But
You subtract the normal component, right?
yeah, this is subtracting the
Yeah.
normal component.
That's a d xi, d alpha xi. I guess d alpha xi.
You want to put the derivative here?
Yeah. Is it?
I switched it. So originally you have a minus sign. Originally you have a minus sign and the derivative on this guy. But because c is perpendicular to u, I switched them
Yeah.
at the cost of a minus.
Yeah.
It's the same. It's the same as this.
Yeah. It's the same.
These are equal because c dot u equals 0. Because this is perpendicular to this.
Okay. Thank you.
Glad you're paying attention. All right, so our task for today is to understand something about the dynamics of this strange-looking PDE. Probably the very first thing you should observe. Well, there's two things we should observe. Which first, let's say, yeah, okay. Okay, conservation laws. So, Schrödinger map equation, at least formally, conserves the energy. That's easy to see because of its Hamiltonian form. So if I take a solution, differentiate the energy, what will I get? I'll get E prime, inner product. Oh, I should put my arrows on. And if I use the equation, expression, and since J is a 90-degree rotation, these two vectors have to be orthogonal. Energy conservation follows from the Hamiltonian form of the equation. And if I put in dissipation, then the energy dissipates. So Landau-Lifshitz, heat flow, dissipate the energy. So that's one of the obvious differences between these two equations. Scaling. Scaling is always important. How does this equation scale? Well, if I scale x by s and t by s squared, that preserves the Schrödinger map equation. Also, the heat flow in the Landau-Lifshitz. You want to do the wave, you have to put balanced scaling on x and t, of course. But also the energy. Because I'm in dimension 2. Everything here is for dimension 2. And this is the reason everything is for dimension 2. Because that's the dimension where the energy is invariant under the scaling of the equation. So that means these problems are so-called energy critical problems. And anyone with experience in this business knows that the critical scaling problems have interesting features and typically lie somehow on the borderline between different kinds of behavior. In this case, on the borderline between blow-up and global existence. These problems are energy critical. Next item of business, since we want to describe dynamics, first thing you should look for are static solutions, time-independent solutions. These are called harmonic maps. And in fact, in 2 dimensions like this, the harmonic maps are complete, the static solutions are completely understood. Static solutions are critical points of the energy, also known as harmonic maps. And now I want to show you a little trick which shows why we understand the harmonic maps completely in 2 dimensions. Let's look at this energy again. Here it is, just the gradient squared. I'm going to rewrite it in the following way. I'm not finished yet. Okay, if I expand this square, I'll get the d1 squared. J is a rotation, it's an isometry, so I'll get the d2 squared. So that's the energy. And then I'll get a cross term. So I have to cancel out the cross term. Now let me give you an exercise. Here's the exercise. It has 2 parts. The first part involves this quantity. So the first part is to show that this quantity not sure about the sign, so I'll put an absolute value to be safe. Is exactly the degree of the map. So if you don't know what I mean by degree, informally, the degree is the number of times that the map covers the target, covers the sphere. You have to take into account the orientation, the way in which it covers. So a more precise definition of the degree is to take the volume form on the target sphere, pull it back by the map so that you're on R2, and then integrate the pullback. That will give you an integer. Well, up to a volume factor, it will give you an integer, and that's the degree of the map. And so the exercise is to show that this quantity here is exactly up to assign the degree. What that shows us in particular, since this quantity here is manifestly non-negative, that tells us that the energy has a bound from below by this quantity. So that if my map is topologically non-trivial, in the sense of having a non-zero degree, then it can't have small energy. Energy is bounded from below by the topology. The second part of the exercise is to figure out when this inequality is saturated. In other words, when this quantity is zero. So this PDE here, I claim, if you were to do a stereographic projection, okay, so stereographic projection is when you take the sphere, you sit it on the complex plane, and then you project all the points onto the complex plane. So then, after stereographic projection, I can think of a map from R2 to C, or from C to C. So what would this equation be as a map from complex plane to complex plane? It could only be the Cauchy-Riemann equations. So this is Cauchy-Riemann. Depending on the sign, it's for holomorphic or anti-holomorphic. Or I guess maybe we should say meromorphic. So for meromorphic or anti-meromorphic. So there's no mystery about what the harmonic maps in this problem are, the static solutions, because they're just pullbacks under the stereographic projection of meromorphic or anti-meromorphic functions. You can essentially say explicitly what they all are. But for us, the most interesting thing is this bound from below on the energy in non-trivial topology. Okay, now, so we have some static solutions. We want to study the dynamics. We want to study the Cauchy problem. For all these equations, but in particular for Schrödinger maps. So that's this system here. With some initial condition. Where do we take the initial condition? Well, at the very least, everything I say here, I want to have finite energy. At the very least, finite energy. So another way of saying finite energy is the space H1 dot, since the energy is just the integral of the gradient squared. And then usually when you're faced with a Cauchy problem, an initial value problem, you first ask if you have any kind of local Wapos, so a solution locally in time, and then you ask about global Wapos. So already when you look at this, this problem, it's still somehow lacking the optimal local well-posedness theory. I mean, there are many results about local well-posedness. In fact, going back quite a long time, so there's a paper Sulem and Bardos, sort of ahead of its time in the 80s, which proves some local well-posedness result for this equation. When you take initial data, now you have to be careful. Remember that our functions, they're not functions, really they're maps. They take values not in a linear space, they're taking values in a manifold. So what we're going to do is we're going to subtract off some point on the sphere. So I'm taking arbitrarily choosing the North Pole. So here's the North Pole. That's just the unit vector k. So if, after subtracting the value at infinity, if you like, you have something in some sufficiently large Sobolev space, then at least locally in time you have a solution to this equation. And this is certainly far from optimal in the sense of regularity. And there are a number of results for this equation and related equation. For example, this one from 07, which lower the regularity to say something like H3, which is still pretty regular. And the point here maybe is that it seems like there is still no good, in general, result for energy space initial data. There's no general, general without symmetry assumptions, which I'm going to make shortly. No general local well-posedness result in the energy space that I know of. Energy, I mean H1 dot, the energy space. Which is sort of discouraging, because whenever you have a scaling critical, like an energy critical problem, first thing you'd like to have is a good initial data, a good local well-posedness theory in the critical scaling space, which we just don't have. Although people are working on this, so there's some at least related results in some recent papers of Smith and Dodson. But for now, no good local well-posedness theory in the energy space. What's a bit better is the small data theory. So there is a good small data theory. So this is small data in the energy space. So small energy, global well-posedness. Was proved by Bejanari, Ionescu, Koenig, and Kotaru in, I'm not sure, maybe 2011. So more precisely, if you take initial data, which is, well, we still require it to have some, if you like, spatial decay. But smallness in the energy space. Then there's a unique global solution. So this, if you're familiar with this business, it might look slightly strange that you have a good, reasonably good small data theory, but not really a good local in time theory. In many situations, the small energy theory is somehow a natural outgrowth of the local in time theory when you have a scaling critical problem. But at least superficially, you can get an idea of why small data might be easier than even than local well-posedness, because when you have small energy, then you have no topology. If you have topology, the energy can't be small. So this is automatically a topologically trivial situation. Whereas if you want to build a good local well-posedness theory, you have to allow for topologically non-trivial maps. And so there's no way you could have a sort of smooth connection between the small data and the local well-posedness theory, because this, if you like, they're topologically disconnected initial data. The initial data here and the initial data here can't be connected smoothly. Okay. So the Schrödinger map problem is an energy critical problem, and you have global well-posedness if the energy is very small. And so you can guess what is the next question. Okay, what if I raise the energy? Do I get global well-posedness for higher energies, and how high? And if you think about it a little bit more, you think, well, okay, I should say something else. It's a unique global solution, but it also scatters. In some sense that I don't want to make precise here. So it goes to 0 at time infinity. So if you think about what solutions we know that don't go to 0, well, those are the harmonic maps. So at this point, the only obstacles we know of for this kind of global behavior with scattering are these non-scattering solutions, which are the harmonic maps. So you would expect that the non-trivial harmonic maps of lowest energy would provide the natural energy threshold for global well-posedness. So that's an open problem. As far as I know, still an open problem. People are working on it, of course, but it's open. And I suppose it's quite hard. So the lowest, I put 2 here. I think it's actually 4. Right. So the lowest harmonic map energy is 4 pi. Okay, so that's, as far as I know, a major open problem. I should remark that this situation is much better for the other equations I wrote up there. So this is, so note, this is known. That is, global well-posedness below this energy threshold is known. Well, it's known classically for the heat flow, going back to work of Schrödinger in the 80s. And it's even known for the wave map, due to somewhat more recent work of Servins and Tataru. Maybe 2010 or so, and there's related work of Krieger and Schlag. So that was a major problem in wave maps that was solved relatively recently, but it's still open for Schrödinger maps. Okay, so this is hard. Understand the dynamics in general below the threshold is hard. And so we're going to look at easier problems. So what we're going to do, instead of considering general solutions, we're going to restrict to some symmetry classes where the equation is easier to understand. So there's a natural symmetry class for these maps, and that's the equivariant maps. So I'm going to call a map M equivariant if it has the following form. So now I'm going to work in polar coordinates. So r and theta are usual polar coordinates. The m is an integer, and without loss of generality, I can take it to be a positive integer. M equals 0 would be the radially symmetric case, which I'm going to exclude from this discussion for now, but come back to later. So I take positive integers. And this r is the generator of rotations around the axis of the sphere, so this guy. Okay, so I think it's clear what the symmetry is here. This means that if you do rotations on the domain, that's doing rotations on the target. One rotation on the domain is m rotations on the target. So this is what's meant, what I mean by equivariant. So now let's look at the energy of an equivariant map. And we can express everything now in terms of this profile function v, which depends only on the radial variable. So let me write this as do the theta integration, and what's left, let me call that E of v. And E of v is this expression here. That's the energy of an equivariant map. Now what I want to do in the equivariant setting is I want to do a more precise version of this integration by parts here. Understand the relationship between the energy and the topology of the map. So let's just look at this energy density. Let me factor it in the same way as I did before. Okay, so here in the notation, I'm not going to bother putting the superscripts here anymore. Everything will be with respect to the map V. So the rotation will be with respect to V, projection will be with respect to V, and so on. I'm not going to write it. All right, so if I expand this square, I get this term. Let me put in the 1/2 also. Since J is an isometry, I get this, oops, I don't. But now I do. The square of this guy is this guy, and then I get the cross term. Okay. Here's a little exercise, very small exercise. This expression here, JRV, is the same as projection of the unit vector k onto the tangent space. Again, the tangent space with respect to the map V now. Okay, and then once you have this part of the exercise, you can figure out what this is. It's just, what is it? It's minus V3 sub R. Oh, and by the way, this notation, V3, that just means third component. So I'm expressing my vector in components. Okay, easy exercise. So now what I'm going to do is I'm going to integrate the energy density in this form. So let's integrate, but not over the whole range. Let's integrate from A to B, let's say, with respect to RdR. And so I find that the energy contained on that interval, so I mean, I think it's clear what I mean by this notation. I mean, integrate the energy density from A to B. And then this term here, well, I get my derivative of V3, and that gets, and then I have a 1 over R, but it gets canceled by the R here, and so I have perfect derivative. So I get what? Plus M V3B minus V3A. Oh, plus or minus. Maybe it's minus plus. Let's go with minus plus. All right, and so again, this quantity here is manifestly a non-negative quantity, so I get a bound from below by the jump in V3 between those 2 points. Any kind of transition from one level on the sphere to another level on the sphere will cost me at least, in terms of energy, will cost me at least this much energy. And we get equality in this inequality exactly when this quantity inside here is equal to 0, which we know has something to do with the Cauchy-Riemann equations. More precisely now, it's just a simple ODE, which we can solve explicitly. Maybe that's the next exercise. Yeah, let's have another exercise. Okay. Two-part exercise. first is to show for finite energy maps that this profile function has certain properties. In particular, it's continuous. And moreover, has limits at 0 and infinity. Once you know it's continuous with limits, you can go back and look at the expression for the energy and realize that what's being picked out here is the first two components, V1 and V2. And so these, for finite energy, these are going to have to go to 0. So the only possible limits are the north pole or the south pole. Okay. So this is a very special property of equivariant maps, which fails in general, and it fails even in the radially symmetric case, that you somehow get pointwise control over the function just in terms of the energy. And it's not enough, as you know well, it's not enough just to have this guy. This will not control the L infinity norm. But the combination is enough to control L infinity. So you have pointwise this uniform control on functions in the equivariant setting, which makes the analysis much easier. In particular, without loss of generality, we can assume, let's choose the boundary condition at infinity to be the north pole. So let's assume that V at spatial infinity is the north pole. So my situation is like this. If I look at, say, the third component of the map, I have something which is going to 1 at infinity, and then it's doing something else. And then at the origin, it has to go either here or here. Two possibilities. Second part of the exercise is to solve this ODE system and find the functions, and we know they're going to be correspond to harmonic maps, the maps which saturate this inequality. So let's solve, I guess we know, now that we've chosen the boundary condition here, we can choose the correct sign here, so I guess we choose the minus sign. And so let's solve some ODEs. Your job is to show that the solutions are of this form. For some phase alpha, and some scaling. Remember, the whole problem is scale invariant, so you expect to see scalings here. Some length scale S, where this is an explicit harmonic map profile. Here are the formulas. So that's exercise in solving a system of ODEs. So these are the harmonic maps. They come in in the equivariant setting, these are the harmonic maps. They come in a 2-parameter family, phase parameter and scaling parameter. And what they look like is this. You can see from this inequality that they are the most efficient way to go from point to point, from level to level on the sphere. In particular, the most efficient way to go from South Pole to the North Pole in terms of the energy. Here's one, here's another. This is one length scale, here's one at another length scale. Please. Plus minus. Sorry, is it this expression here that you're worried about? I didn't write it clearly enough, probably. I'm not sure. Plus or minus over R, J, R, V. Oh, I'm sorry. Yes, I'm being deliberately lazy. So when it, okay, you're right. It's this you're worried about, right? Yes. I'm sorry, I didn't write that, but that's there. Yes. Thank you. Any other questions? Okay. All right, so now you can see from this picture that there are 2 possible different topological scenarios to consider. There's the topologically trivial one. Where the map has its boundary condition at the origin is the same as its boundary condition at infinity. Something like this. And here there's no restrictions, no topological restriction for the solution becoming constant at time infinity. So it's at least possible in this picture for the long time dynamics to be approaching a constant. So the natural conjecture here is that if the energy is not too big, now let's think about for a second how big the energy should be. If we believe that the only possible obstacle to global existence, and you could call it scattering if you want, scattering to a constant, is the presence of these harmonic maps. And if in this scenario you want to create a harmonic map, well, you have to go all the way over the sphere, from top to bottom. That will cost you 2m energy. And then because of the boundary condition, you have to come back again to cost you another 2m. So if you take energy which is below that, twice the harmonic map energy, then a natural conjecture is that the solution, you have global appositeness and scattering to 0. Not to 0, I'm sorry, to constant map where it's just the North Pole. scattering to constant. Trivial harmonic map. So as far as I know, this is still an open problem. There's partial result, which I'll explain a bit later. The other scenario is the topologically non-trivial one. Where now the boundary conditions are connecting the North Pole to the South Pole. And now it's clear just topologically that you cannot converge to a constant map anymore. And moreover, it's clear from this inequality that the energy can never be small. In fact, the energy is bounded from below by this jump times m. So the energy now is bounded from below by the harmonic map energy. And the question is, what happens? This is also an open question. But again, there is some partial progress, which I will discuss a bit later. So this is really, this is two kinds of problems. This is below the threshold, and this is above the threshold. And this is above. So now let me tell you the program for the rest of the lectures today. So I'm going to discuss some results on these problems. In the following order. First, below the threshold. Second, above but only slightly above. Slightly above. And then at the end, if time permits, well above threshold. The threshold here is given by the smallest energy harmonic map that fits in the boundary conditions. In this case, it's twice the energy, twice the harmonic energy. In this case, it's just 1 times the harmonic energy. Now is a good time to ask questions if you have any. Other times are also good times to ask questions. Right. Okay, so let's talk about the below threshold. So as I said before, this is the general below threshold problem where you have no symmetry restriction. And it's still open as far as I know. And then there's the corresponding below threshold problem in the equivariant setting. Notice that the two problems are a little bit different because the energy thresholds are different. This is the harmonic map energy, whereas this is twice the harmonic map energy. That's because of the boundary conditions you have in the equivariant case. You don't have any corresponding thing in the general case. All right, so let's consider just the equivariant setting, but even maybe simpler than the equivariant setting is purely radially symmetric. So let's start with discussion of radially symmetric solutions. So that means I want to solve the following problem. So I have a function now, a map, which depends only on R and T. And I want to solve Schrödinger map equation, which in the radial setting I can write this way. This is just the covariant Laplacian in radial symmetry. And then I have an initial data which is at least in the energy space. As a function on R2. So that's the radially symmetric Cauchy problem for the Schrödinger map equation. All right, I said it's below threshold. So what's the threshold here? There is no threshold because there are no non-trivial radially symmetric harmonic maps. So the threshold energy is infinity. So there is no non-trivial radially symmetric harmonic map. And so there's no threshold. There's no reason not to expect global well-posedness and some kind of scattering for all energies of the radially symmetric. Okay, and that's what I claim happens. So let me state you a theorem. Proved with a student a few years ago. So let's take initial condition for this problem, which is in some space which is appropriate for existing local well-posedness theory. So something like this will do. H3 or maybe H2, I'm not sure. Let's say H3 to be on the safe side. That's certainly not optimal. But the point is that you get global well-posedness. Which lives in the same class for all time. And moreover, you get some kind of scattering. At this point, I can't exactly say what the nature of the scattering is. I'll mention that later. But at least you have some global space-time bounds on the solution, like the following. Okay. What I'd like to do before we take a break is to give just a sketch of how this theorem is proved, because at least it gives you some flavor of how you can analyze geometric equations like this in a very simple setting of radial symmetry. Okay, so let's do a sketch. Okay. So the way this proof begins is important because it's the way all proofs for geometric equations begin, and that's with orthonormal frames. So we need to express the map in some nice way. Because after all, if it's a map, it doesn't even lie in a linear space. It lies in a manifold. And we much prefer to work with linear spaces. Of course, you could try, if you want, you could try to put a coordinate system on the manifold, on the sphere. That might be okay if your map did not cover the entire sphere. But if your map covers the entire sphere, then your coordinate system is going to go bad somewhere. So that's not such a great idea in general. Instead, what people do is they take derivatives. So you take a derivative of a map. Remember from before, when you take a derivative, it lies in the tangent space. Tangent space is a linear space, at least. But of course, it changes. The tangent space changes as you move over the manifold. So what you want to do is you want to pick some orthonormal frame on all the tangent spaces and express derivatives of the solution of the map in this orthonormal frame, and then you have a usual function. The coordinates will be a usual function, and you can do usual analysis. So we're going to do some orthonormal frames in this very simple setting of radial symmetry. So here's what we do. We choose a unit vector, which will depends on the map, so it depends on space and time, which is in the tangent space to the map, to the sphere at the map. Okay, unit. Just choose one such. Okay, so let's work. So the point of view we take here is that we're going to think about doing a priori estimates. So just suppose you have a smooth solution. I changed from U to V, but it should be U. Sorry. Probably can't tell the difference between my U and my V anyway. Okay, so suppose we have a smooth solution, and let's do this construct. All right, so we have one unit tangent vector field, and then we can get a second one, which is orthogonal, just by doing the 90-degree rotation. So then E and JE are an orthonormal frame. They're in particular an orthonormal basis on each tangent space. Okay, and then we're going to take derivatives of the equation. Well, there's really only one that we need to take, and that's the radial derivative, and express it in this frame. So let's express U sub r, which remember is a tangent vector, in this frame. So that's in this frame. So we can write it this way. Let's make a complex function Q by taking the dot products. Like this. So that's a complex valued function. Is the coordinates of the derivative of u in the orthonormal frame. Good. Now let's use the equation. This equation, so let's call this SM rad, radial Schrödinger map. Let's use this equation to find an equation for this now usual complex function Q. All right, so here's the equation. I'll write it again. Let's apply to both sides covariant the radial derivative. Here's another very small exercise. First, covariant derivatives commute with usual derivatives. Second, rotation commutes with covariant derivative. There's maybe a third one coming soon, so I'll leave some space. Okay, so I can use those facts. Reverse the differentiation here. And now the way I'm going to write this combination of dr and dr plus 1 over r is to recognize that this operator is actually the adjoint of this one, because we're working in two space dimensions with radial symmetry. So when I do integration by parts with dr, because of the rdr, I pick up 1 over r. So this up to a minus sign is the adjoint of this. So I can write, in fact, this. And this is a very simple version of something we see again and again when we work with these geometric equations. There's a lot of structure here. And in particular, we always have these factorizations. The operators are always factoring into adjoint and operator and its adjoint. This is sometimes called supersymmetry. Or this form of operator is sometimes called supersymmetry. But anyway, it's a very useful thing which comes up in these geometric problems a lot. Okay. So I need to turn this into an equation for the coordinates q, which means I have to understand how to differentiate u sub r. Well, when I differentiate u sub r, derivatives will land on the q, but they'll also land on the orthonormal frame. So I need to know how to differentiate let's say dr of the frame. So what happens? This is a unit vector, always a unit vector, and so its derivative has to be orthogonal to the vector itself. But this is also a covariant derivative, so it's a tangent vector, so it also has to be orthogonal to u, has to be in the tangent direction. So the only possibility is that this is some multiple of rotated e. So this is some function, let's call it t je. So this is really just the definition of the function t. And same with the time derivative. Back here. I know how to do these derivatives. So dt on UR, in terms of its coordinates are q. I'll get the derivative of q, and then I'll get plus t. And since this is rotated, I'll get an I. So it's easy to check. You get this expression for the coordinate function from this equation. Sorry, J. It's J. Yeah, that's right. So the name of the game is to analyze this equation instead of the original one, which is an equation for a usual complex function, q, and it's starting to look like a Schrödinger equation. Since I have this term, if I put the I over here, I have I dt, and over here I have something like Laplacian. So it's starting to resemble a Schrödinger equation. The next thing to do is to use so-called gauge freedom. So far I just said take any tangent vector field and go from there. But of course you have many choices of tangent vector field, and so you should choose one which makes the equations look good. This is called gauge freedom. And so let's make such a choice. Let's choose to remove this function t, i.e. this equation here. This is sometimes called, well, this is a gauge choice, and in particular this one is sometimes called Coulomb gauge. Believe you can do that, and of course you have to check that you can. Then you can rewrite this equation in a nice way. Let's multiply through by I. And we get this equation. So this is now a Schrödinger equation. Here's the usual thing. This is basically Laplacian, although the factors are reversed, so it's not quite Laplacian. And this is some potential, and we have to figure out what this potential is. So the last step is to figure out the potential, S. 1, 2, 3. This is step 4. Step 5. And this is where the so-called curvature relation comes in. Okay, so let's see. What I'm going to do is I'm going to compute the commutation of these two covariant derivatives. So that's curvature acting on E. According to my gauge choice, when the dr hits the E, I get 0. So I have only the dt here. So this is the same as dr dt E. Because of this expression, I can replace dte by sje. So on the left, I have this guy. Again, using this parallel transport condition, this Coulomb gauge. On the other hand, I have the curvature relation, which you can easily work out. This is part 3 of the exercise. Okay, so see left. Let's see, what will we get? We will get ut dot e r minus the reverse. I think. Yep. And then you can work out what this is in coordinates. It turns out to be exactly okay, so this is also part of the exercise. So now we have an expression that relates this potential S with Q itself. We have this SR equals this quantity, which is, I guess it's like this. And you can also rewrite this as this. And we can integrate to get S. I put that back in my equation. Get the following. Now, this looks very, very much like a nonlinear Schrödinger equation, familiar nonlinear Schrödinger equation. In fact, cubic nonlinear Schrödinger equation. So this is basically Laplacian. You manipulate this, you can get rid of this guy. It really is Laplacian. So this is the linear Schrödinger equation. This term here is the usual focusing cubic nonlinearity. And the strange thing is this non-local guy. So let's call this non-local NLS. And the point is to, instead of analyzing this, try to analyze this equation directly, we look at this one. We can think of this as an initial value problem. Q is a coordinate representation of the derivative of V. So Q now is an L2 function. So this is, if you like, this is a so-called mass critical since it's cubic in 2 dimensions, it's mass critical. But non-local. So that trick that I just went through, this coordinate frames business, turning this geometric equation into a more familiar equation for an honest-to-goodness complex valued function. This is something I learned from a paper of Chang, Shata, and Uhlenbeck. Where they called it, they gave it a name, they call it generalized Hashimoto transform. And the reason they call it this is because apparently there is some more or less classical transformation due to Hashimoto for the one-dimensional problem. So the one-dimensional Schrödinger map problem can be converted by a version of this same operation into honest-to-goodness cubic NLS. So without a funny term, real cubic NLS. So cubic one-dimensional NLS. In particular, a completely integrable system. So this is something from the integrable systems literature, generalized to this problem. But really, this is a simple case of what is always done when analyzing these geometric PDEs, because you have to express the map by taking its derivatives and expressing the derivatives in orthonormal frames in order to work in usual function spaces. So this is a simple case of that. Okay. So now there's something, of course, that I am brushing under the rug that I'm ignoring. I showed you how to go one way, so to go from the Schrödinger map equation to this NLS type equation. I didn't show you how to go back. It's somehow more difficult, but turns out that if you have a sufficient regularity, you can also go back and create a Schrödinger map from a solution of this equation. Or if you prefer, and in fact this is what we do, if you prefer, you can just think of this equation as a method for getting a priori estimates on this guy. So you have some kind of local well-posedness theory for this one. Given this solution, you can construct this one. You can do estimates over here, and then contradict possible blow-up over here using those estimates. So either way, it suffices to prove global well-posedness for this equation. So that's really the theorem, is that we have global well-posedness and scattering for this non-local NLS. Okay, so there's just time to say quick words about the proof. Okay, so by now it's well understood in the literature how you try to prove global well-posedness and scattering results for critical equations. There's machinery that's been developed due to many people, including principally Koenig and Merrill. So the idea is to use the Koenig-Merrill type reduction to a minimal, say a minimal non-scattering solution, minimal mass to be precise, or minimal L2 norm, non-scattering solution. So you suppose you want to prove that all solutions are global and scatter. You assume that's false. Argue by contradiction. Find the smallest L2 mass for which the statement fails. And construct using concentration compactness techniques a non-scattering solution at that critical mass level. But more precisely, we use the Koenig-Marl reduction as done by Philip Tau and Vizan. So as in Philip Tau Vizan of what? 09. Philip Tau and Vizan considered this equation without the non-local term, and either you have to change the sign of the local term to make it a defocusing, or else you allow it to be focusing and you work only for L2 norm below the soliton, because in that case, if I just remove this, I have solitons. Okay? But if I were to change the sign here, I have no solitons. You can get scatter. Okay, so this is for the local version of that equation. So what does the reduction to minimal mass non-scattering solution do? It generates a critical solution, a threshold solution. With some properties, special properties. First is a compactness property. Compactness up to scaling. So something like this. This family, up to some scaling, time-dependent scaling function, is compact, or more precisely, pre-compact in L2. So if you take sequences of these guys, you have convergent subsequences in L2. So this is certainly not a property of general solutions. This is a property of this minimal non-scattering solution. Moreover, there were refinements of Philip Tau and Vizan to show that Q is somehow regular. In other words, smoother than just L2. So a priori, it's just L2. But this minimal solution has extra regularity. In fact, it's in any Sobolev space you want. And finally, they reduced matters to three possible behaviors of this time-dependent scaling function. So you can consider, it's enough to consider one of these. The one in the middle there, the so-called self-similar one, that's not a global solution. This is a global solution. This is a global solution. This one is not. It says blow up at time 0. Okay, so once you have this is after the concentration compactness and harmonic analysis aspects. What do you do? Well, if you are Philip Tau and the Vizan and you have just usual cubic Schrödinger, you say, well, this solution is more regular than L2. In particular, the energy. There's an energy which is well defined for the local Schrödinger equation. And I can use that energy to rule out certain behaviors. Any kind of blow up, for example. Let's say we're in the defocusing case. Any kind of blow up or so. So from their point of view, once the solution is regular, you can use the higher order conservation law of the energy to understand what's going on. For us, we don't have the energy because we had an energy, but we took a derivative, so the energy became the L2 norm, and we don't know anything higher. So we need something to replace the energy. And so we need to use some kind of so-called virial type identity. Here's an exercise. So formally, what do I mean by formally? I mean, suppose you have a solution of this equation, which is very well behaved, smooth as you like, and with very good decay at spatial infinity. Then I claim the following identities hold. Here is one. First. Second. Okay. So the key observation with these identities is that the right-hand sides of both have a sign. So what that tells you, very roughly speaking, is that this term is beating this term. This is a focusing term. If I just had this, I would not have this identity. This non-local term is actually beating the local term and allowing me to have these virial type identities with a positive sign. Without going into any detail, because there's no time, I can use these identities, or more precisely, I have to use cutoff versions of these identities. So here on this one, I have to cut off spatial infinity. I have to stop somewhere, put some smooth cutoff function. Here I have to cut off the origin. But I can use these cutoff versions of these identities and use the compactness to control the error terms from the cutoffs to eliminate each of these three possible behaviors by comparing the left-hand side to the right-hand side of this identity and this identity. This one is for these cases. Yeah. And this one is for this one. And thus, can use these to show that the only solution with this property is 0. Okay, so I think you've earned a break.